So today, we're leaving Chapter 4 finally. Chapter 4 was similar to Chapter 1. Chapter 1 was a little ridiculous. It had 10 sections in it. Just Chapter 4 had about 6 or 7 sections in it. So we're, like I said, we're moving on into one of those things that is a very important concept here, and that is something called eigenvectors and eigenvalues. And that's where our focus is on in Chapter 5. And these are kind of special type of, quote, vectors that create basis for you guys. So again, the whole time we've been playing with this stuff, we've been kind of accumulating ourselves to the wonderful world of vector spaces and how to define a vector space through bases. We have some trivial bases, the standard bases, like R3, 1, 0, 0, 0, 1, 0, and 0, 0, 1. I mean, that's pretty much broadcasting in the clear. That's not very exciting. Everybody can pretty much read that right off the get-go. But if you start changing the basis, then that actually makes it a little more confusing that you have to keep up with what we call those coordinate vectors that actually map what one vector is relative to the basis and stuff like that. So you want to keep, when you change the basis, it changes the coordinate system, and that's that code theory that I was trying to kind of entice you guys with and why this stuff's so important. Well, another type of basis that we're going to be looking at is something called a eigenspace, which is the eigenvectors of a particular matrix and therefore linear transformation. So coming over here, let's start off with our definitions because this is an introduction to linear algebra, so therefore pretty much redefine some more stuff for you guys. Like you don't have enough definitions to memorize, here's some more. All right, so we're going to be talking about eigenvectors and eigenvalues. Now, how many of you guys in here had differential equations? All right, 2. Heard these words before, eigenvectors and eigenvalues. We talk about those in differential equations when we do a system of differential equations, and those guys help us find solutions. So you're going to see this stuff in future classes if you need to take diff-EQ. We use it in there when we do systems of differential equations. It's part of that systems of equations stuff here. So this stuff does play a part elsewhere. But what makes these guys so special? We never tell you that in differential equations. We just tell you, hey, find the eigenvectors and eigenvalues on this thing and write the differential equation solution. We actually don't go into great detail of why it's so darn important. We do in here. So here's the deal. Teaching through an example. So here's my example that I've written up for you guys. So I've written it up so I can talk to you guys about it. As you copy it down, of course. So recall linear transformations. X is being mapped to A times X. And there's some linear transformation, our favorite letter is T. T of X, I mean, when you take T of X is equal to A times X, where A is a matrix. So in this example, I made it very small. Let A be the 2 by 2 matrix, -1, -2, 0, 3. And let me pick vector 1, -2, and let me pick another vector, x, which is going to be the vector 5, 0. All right. I want you to notice this right here, that when I do A times V, that's the matrix A, -1, -2, 0, 3, times the vector V, which is 1, -2. Row by column. -1 times 1 is -1. -2 times -2 is 4. 4 plus -1 is 3. Row by column, 0 times 1 is 0. 3 times -2 is -6. I get the vector 3, -6. In traditional problems, we're done. We just multiply matrices times a vector, and we're done. But this guy's kind of special because look at these two vectors. This is what I plugged in, the V vector, 1, -2, and this is what I got out, 3, -6. Okay? So I went from 1, -2 to 3, -6. What I want you to notice is this, that 3, -6 is actually equal to 3 times 1, -2. It's like taking this vector, I can pull out a constant, I can pull out the 3, factor out the 3, I'm left with 3 times vector V. This is special. In other words, on this vector right here, 1, -2, this matrix A that I'm playing with, when I multiply it times vector V, it is equal to the same thing as a constant, 3 times that vector v. So this weird matrix actually just played a part of just being a constant times vector v. That's special. Matrices typically don't act like constants. They just transform you all over the place. But what this thing really is doing is it's taking vector v and it has some kind of a constant that we're basically times vector v, which basically it's stretching vector v by a factor of 3. It's just a multiple of this guy. So matrix A is acting like a constant. Matrix A, in our matrix multiplication, actually on these very, very special vectors is acting like a constant multiplied times vector v. That is a wonderful and interesting place to be in. So, now look at this one. Matrix A times vector x. And x is the vector 5, 0. So A again is still negative 1, negative 2, 0, 3. When you multiply it times 5, 0, you get the vector, row by columns, negative 1 times 5 plus negative 2 times 0. I get negative 5, 0. Okay? Row by column. 0 times 5 plus 3 times 0. You get 0. Negative 1 times 5 is negative 5. Negative 2 times 0 is 0. Negative 5, 0 is what our vector I get. And if you look at it relative to the original vector, you can pull out that negative 1, and it's pretty much negative 1 times the original vector, 5, 0. So what does a negative 1 actually do? When you multiply negative 1 times a vector, it gives you the same vector, but it reverses the direction. So it goes the other way. So this is negative x1, which is the reverse of x. If x is going this way, negative 1 will go this way. Does that make sense? So again, the matrix on this very special vector is acting like a constant being multiplied times that vector. Those are special cases, and where a matrix acts like a scalar on a vector. That's the gist of this stuff right here. Now, here's the big definition. An eigenvector of an n by n square matrix is a vector x where a times x is actually equal to lambda times x for some constant scalar lambda. So an eigenvector of an n by n matrix is the vector x. Eigenvector is the vector x where the matrix acts like a scalar. X is the eigenvector. The eigenvalue of an n by n matrix is the constant lambda. We just like to use Greek letters to impress you guys. Lambda, where a times x is equal to lambda times x. So when you have an eigenvector, you also have an eigenvalue. The eigenvalue is the constant that the matrix is acting like, and the eigenvector is the vector that when you multiply it times a matrix, it acts like a constant being multiplied times the matrix. So this is a combination pair. Eigenvector with eigenvalue. Eigenvalue is the lambda, eigenvector is the x. Note that the corresponding vector to the eigenvalue lambda. So x is the corresponding eigenvector to the eigenvalue lambda. They are connected. So, and also remember this. We're going to be looking at the wonderful world of linear transformations. Those things are coming back to haunt you. So, but this is a linear transformation that we're going to take vector space V right back into vector space V. So T of V would be equal to some matrix A times V. So if you remember, when we talked about linear transformations a few sections ago, linear transformations can be written, any linear transformation can be written as a matrix multiplication. So, and with this matrix multiplication, because the matrix is going to be square, it's going to take the vector space right back into the same vector space. So it's, you take vectors from V and you're going to map yourself right back to more vectors of V, okay? So, we have the eigenvector and eigenvalue. These guys are real special. Look, matrices are tough enough as it is because of this row by column crap you have to do when you multiply it out and get your extra new vector and stuff like that. But again, when we're talking about a particular space, a space is defined by its basis. What is a basis? It's a minimum number of vectors, literally independent vectors, that when I span, take their linear combinations, of those vectors, I can get anybody in the space. So it's the minimum number. And the number of those vectors in the basis tell me the dimension of that space or subspace, whatever I'm playing with. We're going to be looking at the wonderful world of eigenspaces. This is the wonderful world of a basis where are going to be the eigenvectors. And in this world of the eigenvectors, that particular linear transformation that maps these guys around will actually act like a constant being multiplied times these vectors. So this is a wonderful place to be in because it makes doing the matrix math easy, because multiplying by matrix A is just like multiplying it by a constant times the vector. Okay? So this is the gist of the wonderful world of eigenvectors and eigenvalues. All right, so how can you tell? So the first thing I got to do, if you learned anything about me trying to do this particular class, is this. Try to give you guys tons of examples, okay? So, and again, read the wording. Hopefully you figured out the wording on my test and my homework sets is just like the wording that I put on the homework sets and the examples I do in the class. So, let A be the famous 4, -2, -3A, classic 2 by 2. Let's start small. We'll do the 87 by 87 matrix later. But right now, just 2 by 2. So A is 4, -2, -3, 9. And let U be the vector 4, 2. And let V be the vector -2, 5. Are U and V eigenvectors of A? Pretty much yes or no, but then you actually have to show your work. So, here we go. Let's first start talking about, let's talk about U. So vector U is equal to the vector 4, 2. The question is U, vector being 4, 2, an eigenvector of A? That's really the gist of the question right there. So, how do I figure this out? Well, what is an eigenvector to a particular matrix? It is a vector where the matrix, when you multiply it, will actually act like a constant being multiplied by my vector. If there is a constant, then it is an eigenvector. If there is not a constant, if you can't be able to factor the constant out and get the original vector back again, then it is not. So let me show you the gist on this one. So let's multiply A times U. That would be 4, -2, -3, 9, multiplied by the vector 4, 2. Okay, row by column. Let's not screw this up. So here we go. 4 times 4, 16. -2 times 2 is, let's see here, -4. 16 minus 4 is 12. Do you concur with my first component? All right, doing math in my head and looking down, and I look at 3 different examples at one time, and all of a sudden the numbers run together. Let's try this again. Row by column. -3 times 4 is -12. 9 times 2 is 18. -12 plus 18. 18 minus 12 is 6. So there it is. What does that tell me? Now, I'm trying to get the original vector back again. Yeah, I know I could factor a 2 out of this guy. Don't care. All I want to do is get the original vector back again and compare to this guy. Now, what do I need to what do I need to factor out of 12 to be able to get a 4? 3. So if I pull that 3 out, that would make this component 4. So 3 times 4 is 12. But if I pull a 3 out of a 6, what do I get? 2. And what I want to show you is this. This is A times U, and what I'll end up getting over here is equal to 3 times U. Matrix A is acting like 3 times U. Does that make sense? So the question is U an eigenvector of A? The answer is yes. The vector 4, 2 is an eigenvector of matrix A. I can tell you more than that. Lambda equals 3 is an eigenvalue of matrix A connected to vector U, because they always come in pair, 4, 2. So lambda equals 3 is the eigenvalue, but the vector 4, 2 is an eigenvector. So the answer to the question is yes. Does that make sense? However, we got another question down here, and that question is this. Is the vector V, which is equal to the vector negative 2, 5, is this an eigenvector of matrix A? Well, all right, so basically we do the same thing. So we come up here, and I'm going to do A times V now. So matrix A was 4, negative 2, negative 3, 9, times vector V, and vector V was negative 2, 5. Let's see what we get. Row by column. 4 times negative 2, negative 8. Negative 2 times 5 is negative 10. Negative 8 minus 10 is what? Negative 18. Agreed? Row by column. Negative 3 times negative 2 is 6. 9 times 5 is 45. 6 plus 45 is 51. Does that make sense? Now, what do I need to factor out of a negative 18 to get a negative 2? So I always look at the first component to see what I need to factor out. What is it? 9. So I'm going to factor out a 9. When I do that, I'm going to get a negative 2, but then I got to factor out a 9 out of 51. What is 51 divided by 9? It's pretty much 51 9. It is not 5 for sure. Does that make sense? So this is what I get. So this is not equal to 9 times vector V. So I just want to show you. So vector V is not an eigenvector of matrix A. So this answer would be no. But you can look at these two examples and see how to do it. I'm doing the exact same thing. If I can start out with a vector, multiply by a matrix, get my solution, and then be able to factor a constant out and get the exact same vector back again, then yes, that's called an eigenvector, and that 3 would be an eigenvalue. But if I have a vector, multiply it out, and I try to factor something out of that first component, but the second component doesn't match up to get the original vector back again, then the answer is no. That particular vector is not an eigenvector. Does that make sense? Did I lose you anywhere? Difficult? No, there's matrix multiplication. But I'm trying to drum into your head what this stuff actually means. Eigenvectors are special vectors. When I multiply an eigenvector times a matrix, I'm going to get a vector that when I can factor out a constant out of it, I'm going to get the original vector that I started with back again. That's an eigenvector. And the constant that I can factor out is called the eigenvalue. Okay? So read the question. This question was, here's a matrix, here's a couple of vectors. Are these guys eigenvectors? The answer is yes or no, but you have to show your work. Well, let me switch up game here and then try this question. This is a little deeper here. Question number 2 asks you this. Oh, same matrix, just to let you know. I just put on a different piece of paper. Matrix A is still the matrix 4, negative 2, negative 3, 9. Is lambda equal to 10 an eigenvalue of A? Answer is yes or no, but then you better prove it to me, okay? So, how would I figure this one out? Remember the last one. Was that one difficult? No, you just did matrix multiplication and you try to factor somebody out to see if you got the same vector back again. This one, well, if, this is how you do it. If lambda equals 10 is an eigenvalue, then there exists an eigenvector. This thing is 2 by 2, so I'm just going to call him AB, because no imagination on this guy. There's going to be an eigenvector, AB, such that A times, and let's call this guy a name. Let's call him V. Just going to give him a name. There's got to exist an eigenvector V, AB, such that A times V would be equal to 10 times V. This is your definition of what it means to be an eigenvector and an eigenvalue. Does that make sense? All right. But A is this, 4, -2, -3, 9. Vector V is this arbitrary AB vector. It's got to be equal to 10 times this arbitrary AB vector. Does that make sense? Which means, wait, keep going here. Which means that if you continue to put this stuff together, this would mean that 4A minus 2B has got to be equal to 10A, and -3A plus 9B has got to be equal to 10B. What did I do there? Multiplied row by column, but remember it becomes an equation, 4A minus 2B, and then row by column, -3A plus 9B. It's got to be equal to, in the top, 10A, and the bottom, 10B. What your goal here is this: solve for A and B if you can. If you can, then you got your eigenvector, which makes 10 equal the eigenvalue. Does that make sense? If you cannot, well, then you're done. Lambda equals 10 is not an eigenvalue. Does that make sense? So you got to be able, can you solve for A and B on this guy, or are you going to get one of those inconsistent systems again? See, everything's boiling right back down to this chapter 1 mess that we always had. And that's the way this class was really designed to be done. So, can you solve this guy? How would you solve this? So come over here. Solve for A and B if you can. 4A minus 2B equals 10A. And I got the equation -3A plus 9B equals 10B. How would you solve for A and B? What would you do? Well, these are equations, and I like to group together like terms. So I'm going to move my 10A to the side because they're just equations. -10A minus 10A. This will give me the equation. 4A minus 10A is what? -6A minus 2B. That's going to be equal to 0, right? And then over here, I'm going to subtract 10B from both sides, combining like terms here. So this ends up canceling. This will end up giving me an equation, -3A. 9B minus 10B is what? -1B is equal to 0. Does that make sense? Now, how would you solve this? Okay, this is 2 by 2. You can go back to the 9th grade and do substitution of equations if you want to. But we are in linear algebra class in college, so therefore, let's use linear algebra. So, using linear algebra, here we go. I'm going to rewrite this guy as a matrix. Now is -6, -2, -3, 1 times A, B, right? And it will be equal to 0, 0. Now you feel better about it? Good. How would you solve for A and B on this guy? What? Thank you. You learned something from chapter 1. We're going to augment this guy. All right? So how do we solve this stuff? You understand, I'm really trying to get this prepare for the final exam thing in your head. Yes, ma'am. It is. There it is right there. Thank you. Okay. So, but I'm trying to get that augmented system into your head in terms of how to solve this stuff. So, this becomes -6, -2, -3, -1, augment 0, 0, and now we're going to do what? Row reduction. What's your first move? How about -1/6? You could row swap, but I'm going to go for not row swapping and just multiply -6 times row 1. Basically, we'll replace row 1 with that. That'll be 1, 1/3, augment, -6 times 0 is 0, -3, -1, 0. Now what's your next move? 3 times row 1 added to row 2, replace row 2. That would be 1, 1/3, augment 0. Now, 3 times 1 is 3 plus -3 is 0. That was the point. 3 times 1/3 is 1 plus -1 is 0. 0 times 0 is 0 plus 0 is 0. Oh, I got a row of zeros. What does that mean? Consistent, infinite. Okay, and the row of zeros means I got an infinite number of solutions. Fine, infinite number of solutions. Okay? If there's an infinite number of solutions, well, at least find one of them for me, please. Well, I would go back to my equation, which is this. This represented A and B. So this tells me that A plus 1/3 B is equal to 0, right? And again, I'm trying to remind you of stuff because you're looking at me like you've never seen this before. Solve for the pivot. So A would be the pivot. A would be equal to, subtract 1/3 B, that would be -1/3 B on the other side. Agreed? Solving for the pivot. And because there's an infinite number of solutions, that means we have what? Free. Who's the free variable here? Would be B. B would be equal to himself. He's free. Okay? So the vector AB will actually be equal to -1/3 1 times B. It's the linear combinations of this guy. And as you said, there is an infinite number of answers. Okay? But the question is there an answer? So because there is an answer, here's the deal. The answer is, does A times B equal to 10 times B? Is 10 an eigenvalue of matrix A? The answer is yes, it is. Does that make sense? And to let you know, down here, lambda equals 10 is the eigenvalue of matrix A, which was this matrix, what was it, 4, -2, -3, 9. And it gets better, the eigenvector is what? What was my eigenvector? Well, it's any linear combination, or in this case, since there's only one vector, any multiple of this particular vector. The vector is 1/3 1. That's the actual vector. You can also make B equal to 3 and make it -1, 3. Or better yet, make B equal to -3. That makes it 1, -3. It's any ratio combination of those two numbers. This ends up becoming the eigenvector. So not only is it an eigenvalue, but if it's an eigenvalue, you should be able to tell me who's it's associated with. Every eigenvalue is associated with an eigenvector, at least one eigenvalue, sometimes more. Does that make sense? So this one was a little more difficult to be able to find whether it's a little more difficult to be able to find is a particular constant, in this case lambda equals 10, is it an actual eigenvector? So you have to multiply it out and then you're back to doing, quote, systems of equations from our old school stuff. Question?
What's the difference between the eigenvalue and eigenvector?
Eigenvalue is the constant that the matrix acts like, so it's going to just be a number. The eigenvector is the vector that you multiply the matrix by, and it's the vector you can multiply the constant by to actually get the same thing. So they are paired. So when you talk about an eigenvalue, there's an eigenvector that's going to be associated with it. When you talk about an eigenvector, there's going to be a constant called the eigenvalue associated with it. So they always come in pairs. And remember, the eigenvalue is the constant that the matrix acts like on the eigenvector. So when we're talking about matrix multiplication, you multiply a matrix times a vector, it'll be the same thing as that constant, which is your eigenvalue, being multiplied by the same vector. So the matrix only scales the actual eigenvectors on this thing. Okay? So let me see if I can explain this a little better from a linear transformation perspective. Okay? So I'm going to deviate from my notes so I can completely mess myself up here. But I want to make sure that you understand the concepts here. All right. So let me just deviate briefly here, and I'll get back to my awesome notes and stuff. All right. Here's the deal. All right. You have T going from vector space V to vector space V is a linear transformation. Okay? What does that mean? Okay, well, we had some properties on linear transformation. We know that T of vector V plus vector W will be equal to T of vector V plus T of vector W. We know that T of a constant times vector V is equal to a constant times T of V. You remember these guys? This was part of your definition of linear transformation. We also had some properties. Here's one. What would T of 0 have to be equal to? Okay, 0, that's part of our properties of a linear transformation. Okay, and of course we had the other property was that T of CU plus dV was equal to CT of U plus DT of V, C last test, first test or whatever it was. Okay, on these definitions and stuff like that. This made us have a linear transformation. But we went from linear transformation from V to W, that was fine. But now, because A is going to be a square matrix, any linear transformation can be represented by a matrix. And we want square matrices. And because we want square matrices, we're going to have the same domain range or codomain, if you will. We're going to have the same vector space going in and vector space coming out. So what does the linear transformation do? When I take a vector V and do T of it, it's going to transform it. Linear transformation. It's going to transform it. So, it does stuff like this. So, I'm just doing two-dimensional. So, here is vector V, okay, in the old XY plane. When I apply T to this guy, right, T of V, I'll get this guy over here, and it'll be something like, maybe it'll do something like this to it. It transformed it. It took this guy, rotated him 90 degrees, and shortened him out by a little bit. And again, this is just a 2x2 case. And if I had 9x9, I can show you all kinds of weird stuff it does. But it's hard to see visually on this stuff. So this is why. So this is what the linear transformation does. It changes up the vectors. It makes them shorter or longer, it rotates it. It does this. Now, T of 0 has to be 0, so you're always starting out at that same little spot there. But it may rotate it, it may stretch it out, it may shrink it up, it may put it into a different quadrant. It'll do something to your vector. Does that make sense? That's what the linear transformation does. Now, any vector space here is the same vector space. When we're talking about the eigenvalues, okay? So if I'm talking about an eigenvalue, so let's let U be an eigenvalue of, eigenvector, better word, eigenvector of linear transformation T. This is a vector here, okay? So let me pick U. U is going to be this vector right here. This is X, here's Y. Here is this very special, there it is right there. There is my vector U. He's real special. U is an eigenvector of T. What the T transformation is going to do to this guy is it's going to do this. It's going to do that to him. What did it do? It shrunk him down. So this would be T of U, and that's going to be equal to some constant lambda times U. So all it did was just scale him back. It could make him bigger, it could make him smaller, it could make him negative and make him go in the other direction, but he's still on that same line. Does that make sense? These are parallel, or they're supposed to look like parallel. Does that make sense? It just scales it back. But all the other vectors in the space, it rotates it, it shrinks it, it stretches it, it beats them up. Only eigenvectors, it leaves them where they're at and just scales them. Maybe negative, flipped it to the other side, but still going to be along the same path. Does that make sense? So these eigenvectors are going to be real special in terms of my space because the matrix that represents the linear transformation will only act on these vectors like a constant being multiplied by the vector. It just scales them back or extends them. Yeah.
You said for the eigenvectors, they can make the transformation like smaller or larger. Did you say it can also like flip it to the other side?
Yeah, -1. What would -1 times vector u look like? -1 times vector u would be basically taking this vector and just moving them to the other side, 180-degree direction. It's still going to be along this line, it's just going in the other direction. That's what a negative does. A negative is they basically reverses the direction, but it does, I mean, and so it just, but it's still along the same, if you think about this being a line here, you know, it's still going to be along that line. There's a line here, but in terms of how far it goes, this scaled it back. And the scaling back of it is how by how much is that lambda. So these are very special vectors within your space that the linear transformation actually acts like a constant. So again, why is this important? Well, you see this kind of stuff in differential equations, and we talk about solutions and that, but I won't go there since most of you guys haven't had that class yet. But here's the other deal. I mean, these guys, now let's talk about what I'm trying to motivate you guys on, because like 90% of my class in here are all computer science majors, okay? So what's the big deal on why you want to know this kind of stuff? Well, what is this whole purpose of this transformation? What do you typically do with these kind of transformations? Well, one thing I would like to do is code things and decode things and hide things so hackers don't find the stuff, but I can put my credit card numbers in it or my bank account numbers or whatever the case may be, okay? So if I got this basis, which is what sets up my whole system, if I look at the basis of this vector space, and I don't want to make it the standard basis, that's in the clear. That's like broadcasting my credit card numbers, 10001 and 001. That's not very exciting in terms of a basis, but it works. Those are the easiest. That's your standard, easy basis. What we want is a convoluted basis, so that makes it difficult for the hackers. Because, you know, understand, oh yeah, how many digits are on my credit card number? Well, let's see here. I typically have 16 digits, 4, 4, 4, 4 grouping. Then I've got the, let's see here, what else do I got? I got the expiration due date, and I got the CVC code in the back of it, and all this stuff. So all this stuff are digits, 0 through 9, that I want to be able to change. Okay, so what do we got? 16 plus, let's say, 4 more, no, yeah, 4, 6 more, 16, 6 is 22, plus my 3-digit code, 25 digits now. So we're talking about R25, right? Okay, that's my space. So now it's getting quite large. But I want to be able to transform it. When you give me your credit card, I want to transform it so it's going to turn into some other kind of number that nobody can figure out what this number is. It's kind of hacked, it's kind of messed up over here. But if I can go forwards, I should be able to go back and get my credit card number back in the clear. But if a basis kind of helps me figure out what the transformation is going to be, what I would like to have to be the basis that the hackers don't know about is my eigenvector, eigenvalue space. Because I got all these different vectors going on here, but the very special vectors, it just scales them back. All it does is change it by a constant, but I get the same vector back again. So from my understanding, this will be easy for me to manipulate, but it'll be a nightmare for the hackers because they think it's being switched all over the place, but I know where the special ones are at. They're going to basically just scale. So what I'm looking at in layman's terms with you guys is something called the eigenspace. I'm showing my hand on chapter 5.3 here, but eigenspace, it's a space, which means I'm going to have a basis, but my base is going to be consisting of the eigenvectors, not just any kind of vectors, but the eigenvectors. Does that make sense? That's what I'm kind of setting you guys up for and stuff. So let's continue on with my awesome lecture. But hopefully that kind of helps you make sense out of the situation here. So here we go. More definitions. Given a square matrix, and that's the one thing I wanted you guys to emphasize on, is I'm only finding these eigenvectors and stuff. You can only find them from the square matrix because we were talking about linear transformations, and we got to go from the one vector space to the same vector space. Okay, so talk about an automorphism. You're going from the one vector space to the exact same vector space. That makes square matrices on that. So given a square matrix A, the collection of all eigenvectors such that A times X is equal to lambda times X for some constant lambda, the eigenvalue, is called the eigenspace. Now, it's a space. And what makes a space? All right, so again, it's one of those things that people have a difficult time with. And I try to put some of those kind of questions on the homework type thing here just to try to mess you people up. But here's the deal. A space is got to have the word span in front of it. A listing of vectors is just vector, comma, vector, comma, vector. Okay? You remember that one. Vector, comma, vector, comma, vector. Oh, so an eigenspace is the span of the eigenvectors. This will be called the eigenvector. So you're going to have some eigenvectors, but that doesn't make it a space. That just is a listing of vectors. To make it a space, span. What does the word span mean? A set of linear combinations of the eigenvectors. This will be called the eigenspace. Okay? So let me see if I can go back here. Since I brought it up, and I had lots of people come by my office about this one. Let's see if I have it somewhere up here. Let's see here. Homework number 4. Here it is. Let's see if I can have it. This is the one, homework number 5 on chapter 4. It was this problem right here, okay? It was a weird little question. I believe it was question number 4 on my homework. People were looking at me like I'm strange, but no, I was trying to make a point. Vector V1 is 1, 0, negative 1. V2 is 2, 1, 3. Vector 3 is 4, 2, 6. W is vector 3, 1, 2. Is W in V1, V2, V3? Is 1, 0, negative 1, is that W? No. Is 2, 1, 3, is that vector W? No. Is 4, 2, 6, is that vector W? No. W is not in that set. There is no span in front of that word. It's just a set of vectors. Is this W? No. Is that W? No. Is that W? The answer is no. It's a stupid question, but I'm trying to make a point. You'll see the point in just a second. How many vectors are in V1, V2, V3? Yeah, 3. Don't hurt yourselves. 3. Okay, 3 vectors there. Okay. How many vectors are in the span? Now I chucked the word span in front of this sucker. Okay? Now how do you figure out how many vectors are in the span? The span makes a space. And what defines a space? A basis. And a basis is what kind of vectors? Linearly independent vectors. And how do I tell which ones are going to be linearly independent? I'm going to take basically a matrix of column vectors, 1, 0, negative 1, 2, 1, 3, 4, 2, 6, put them in columns. I'm going to row reduce that sucker, and I'm going to count how many pivots I have. I'm going to look for the pivots. Does that make sense? That's what I'm supposed to do. And then, and once I do that, okay, I can sit there and figure out the basis. But this question is this: how many vectors are in the span of V1, V2, V3? How many vectors in this thing? What does span mean? Linear combinations. How many vectors can you get from the linear combinations of V1 added to V2 added to linear combinations of V3? What's the answer? Infinite number. There's an infinite number of vectors in the span. There's only 3 vectors in the set. That set, that span means linear combination. That's infinite. But now, here's what I'm talking about in terms of those pivots. Is W in the subspace spanned by these guys? Well, from this guy, I can figure out if they're linearly independent or not. Maybe a space, maybe they're not. I only need 2 vectors or whatever. But for W to be in the subspace spanned by this guy, is there a constant that I can put in front of V1? Is there a constant in front of V2? A constant in front of V3, where that would be equal to the W vector? If you can find A, B, and C constants, then it is. If you cannot, it is not. Does that make sense? This is what I'm after with this stuff. A set of vectors versus the span versus the space. Yeah.
So for B and A, that's just for the like the sake of like understand like what you wouldn't really it would be like C would be the one that you have to solve for like.
Yes, yes. This one is actually solved. This one is just, is W in this set? It's a stupid question, but no, that's not W, that's not W. It's V1, V2, V3. W is way over here, it's not in the set. Okay. Is, how many vectors in the set? Now, again, there are 3 of them, V1, V2, V3. But how many vectors are in the span? That's throwing that word span, understanding linear combinations. And when you do linear combinations of a set of vectors, there's always an infinite number of things. Why? Because it's a linear combination. You can multiply any constant times one of the vectors, add it to another. How many constants are there out there that you can multiply by a vector? All real numbers are, right? So there's an infinite number of constants, therefore there's an infinite number of vectors in a span. That's what I'm after. But then to show if V is inside this guy, you've got to come up with the what constants do I need to multiply times these vectors to be able to get W out of it stuff. Okay. So back to this, back to our space now. Again, my goal here is to kind of tie all this stuff together with you guys to make sure you understand it. So now we're going to be talking about an eigenspace, where an eigenspace is where you take the eigenvectors and make those the basis. Okay? Theorem. The eigenvalues of a triangular matrix are the values on the diagonal. We'll prove this later. But if you got a triangular matrix, now help me out here. What's a triangular matrix? There's 2 types of triangular matrix. There is the, I'll put it up here, there is the upper triangular matrix, and there is a lower triangular matrix. Now, we did that stuff when we were playing around with that LU decomposition on a particular matrix and stuff like that. Remember the old LU decomposition of a matrix A? Well, upper triangular, remember these guys are going to be square, so you're going to get numbers on the diagonal, okay? And upper triangular means you got numbers up here, okay? But they're going to be zeros down below it. That is an upper triangular matrix. A lower triangular matrix is you get numbers on the diagonal, and you get numbers down below that main diagonal down here. So these are numbers, but above the main diagonal, you get zeros. Does that make sense? But in either one of these 2 cases, that diagonal is where the eigenvalues are going to be at. And keep going. And again, we will prove this theorem next time for you guys. All right, but here we go. Theorem. If V1, V2, VR are the eigenvectors of a square matrix A, and they correspond to a distinct, now I underline this word distinct, the book does not, to let you guys know, to distinct eigenvalues, lambda 1, lambda 2, lambda r, then the set of V1, the set of vectors V1, comma V2, comma VR will be linearly independent. What was the key word on this particular theorem? We know that for each eigenvector, there's going to be an eigenvalue. Does that make sense? Eigenvector connects to an eigenvalue because A times V is equal to lambda times V. The V is the eigenvector, lambda is the eigenvalue. If you got all these eigenvectors right here, and they are connected to an eigenvalue that are distinct. You know, 2 is not the eigenvalue for V1 and V2. We're not talking about that case. We're talking about for every eigenvector, there is a distinct eigenvalue for these guys. Then I can automatically tell you that the set of eigenvectors are going to be linearly independent. We're setting you up for that definition of a basis. What is a basis? It is a linearly independent set of vectors that quote-unquote span the entire space. All the linear combination of those vectors will give you any vector in the space. That's what a basis is, okay? So, with that being said, our goal now is to find, how do we find these elusive eigenvectors and eigenvalues so we can find these spaces that we're going to be creating? Well, that leads us into section 5.2. Okay? Section 5.2 starts out with this guy right here. We're going to have something called the characteristic equation. Again, if you took differential equations, you have heard this word before, at least you should have from your professor for teaching DFEQ. The characteristic equation, given T, is a linear transformation from vector space V to vector space V. T goes from V to V, such that T of vector X is equal to A times vector X for some matrix A, which is n by n. It's got to be square because you're going from the same vector space to the same vector space. That'll always make a square matrix for your linear transformation. Then the eigenvalue and the eigenvector corresponding to the linear transformation T, or matrix A, are the vectors V and lambda such that AV is equal to lambda V. Okay? This is what we mean when we're talking about eigenvectors and eigenvalues. Matrices times a vector is the same thing as a constant, lambda times that same vector. All right, so here we go. From this, we're going to create the characteristic equation. Here we go. So, follow along because this is important. And this is the kind of thing that I make my graduate students actually prove to me when they have to go through their orals for getting their master's degree. This is a classic question. It takes a few seconds to do it, but it's a classic one. First off, how do you get a characteristic equation? Could you prove to me where the equation comes from? And here it is. Well, a characteristic equation is where the eigenvectors and eigenvalues come from off of a matrices, which represents a linear transformation. So as A times vector V is equal to lambda times vector V, then A times vector V minus lambda times vector V would be equal to what? I move this to the other side. What's it going to be equal to? 0 what? 0 constant or 0 vector? You said it. 0 vector. There's got to be a 0 vector, so we're going to be very precise with this stuff, right? Because this is a vector. This is a vector. When you multiply A, n by n times n by 1, it's n by 1. V is n by 1 times constant, still n by 1. So you can pull them to one side. It's going to be equal to 0, but it's going to have to be a 0 n by 1 vector. This is matrix vector stuff, vector equations. Okay. Now, you want to solve for V on this thing. What do you notice about V? It's in both these two terms, right? So traditionally, we would like to factor it out. Agreed? And factoring is perfectly legal in linear operations and stuff like that, but here's your problem. What does A represent? Matrix. What does lambda represent? Scalar, constant, excellent. You can't factor them out because these are non-like terms. It's just when I multiply this, I get to the same area that I can multiply constant times this. So to be able to, and this is the trick, to be able to combine like terms, I have to do this. Matrix A times vector V would be equal to turn that scalar into a matrix scalar minus lambda times I times vector V. That's equal to 0, where I is the n by n identity matrix. That right there is the trick that my grad students have to show me. To be able to combine like terms, you've got to be like. One's a constant, one's a matrix. That is not like terms. But a constant can be viewed as a constant times a matrix. So when you multiply lambda times I, it becomes a matrix, but the lambdas only show up on the diagonal where the ones are at, zeros everywhere else, and 1 times lambda is lambda. So this lambda times I turns into a matrix with just lambdas on the diagonal and zeros off the diagonal. So because of that, now they are like terms. I can do this. Now, these are both matrices. I can factor out the V. Thus, A minus lambda I times vector V would be equal to 0. But I had to do that first. That was an important trick or mathematical concept in terms of being able to manipulate my equations. Now, here's the deal. If I wanted to solve this guy, this is now a matrix. What happens when I take a matrix, multiply it times vector V, and I set it equals 0? Now, here's the deal. V is an eigenvector. Okay? Not zero vector. I want it to be a real vector. Zero vector really doesn't work for me. Okay, yeah, great. Lambda equals 0. It could be an eigenvalue, but the typical eigenvector is going to be 0, or pretty much anybody you want, because 0 times anybody is 0. So what we want is these non-zero vectors and non-zero lambdas that we're looking for and stuff. Yes, you can have lambda equals 0 as an eigenvalue, but still, what I want is the vector not to be the 0 vector. So if this is not 0, but when I multiply it times this matrix and I get 0, that's going to enforce that this matrix here minus lambda I is singular. All right, throwing more words at you. What does singular mean? Non-invertible. Okay? This part right here, times V, has got to be singular or non-invertible. What are some properties about matrices? This is a matrix now. A minus lambda I. It's a matrix, but it's not invertible. Non-invertible means singular. We had a property about this stuff, tying it back in with other things you've had before. What does it mean? It means this. If it's singular, when I take the determinant of A minus lambda I, because it's non-invertible, can't find an inverse of it, called singular, what does the determinant of a non-invertible matrix have to be? The determinant of a non-invertible matrix is 0. And if you've got a matrix and you need to check, square matrix, and you need to check whether it's invertible or not, you take its determinant. If the determinant of that square matrix is not 0, it's invertible, called non-singular. If the determinant is equal to 0, it's not invertible, called singular. So this is a singular matrix, which means that the determinant of the A minus lambda I is equal to 0. And therefore, the characteristic equation of a matrix, also known as linear transformation. A is the determinant of A minus lambda I equal to 0. That is an equation. That's called the characteristic equation of a matrix A. Okay? And it basically stems from the definition of eigenvector, eigenvalue, and how we have to mathematically put it together so we can get to be able to solve, because this is going to help us figure out who the eigenvectors and who the eigenvalues are. Okay? So, hang this good stuff together here. Here we go. Again, emphasizing this so I can do an example. I want to highlight from, now we're in section 5.2 here. Again, some stuff that we can actually prove to you guys. So I've rewritten them again, but here's one theorem. The eigenvalues of a triangular matrices, whether it be upper or lower triangular, are the values on the diagonal. Focus on the diagonal. If V1, V2, Vr are eigenvalues of the corresponding distinct, and that's the word I want to emphasize, distinct eigenvectors, lambda 1, lambda 2, lambda r, then the eigenvectors V1, V2, and the Vr will be linearly independent. We're going to be setting you up with this concept of basis. And if I know I've got distinct eigenvalues, I don't have to do anything. I can declare, put a stake in it, go, this is a set of linearly independent vectors, which therefore I can form a basis off of. How do I find eigenvectors and eigenvalues? Well, this is what we just talked about. So A is going to be an n by n matrix such that AV equals lambda V. Then lambda is called the eigenvalue. V is called the eigenvector. When lambda, so AV equals lambda V, that means AV minus lambda V equals 0, which means AV minus lambda V equals lambda times I times V. You have to insert the I matrix so you can now have matrix multiplication. Factor out the V, and because it's equal to 0 and the A minus lambda V will be a non-invertible matrix, singular matrix, the determinant of A minus lambda I equals 0. And the determinant of A minus lambda I equals 0 is called the characteristic equation. There's the whole ball of wax right here. This is how we're going to do it. Okay? So, here we go. You know I got an example waiting for you, but I have to come up with all the theorem stuff first. So, here we go. So this is an important problem because this actually begins the gist of how to solve these particular guys here. All right. Here we go. Something small. Always start you out small first. Don't worry. The 12 by 12 is coming in a second. Let A be the matrix 2, 1, negative 1, 4. I want you to find the eigenvalues and the eigenvectors of this matrix A. Well, the first thing you want to do, you want to have steps. I'll give you steps. If you're trying to find the eigenvalues and eigenvectors, eigenvalues and eigenvectors of a matrix A, the first thing you want to do is step 1 here is find the characteristic equation. What is the characteristic equation? It is the determinant of A minus lambda I is equal to 0. That's what you need to have memorized. Determinant of A minus lambda I equals 0. So this would be the determinant of matrix A, which is 2, 1, negative 1, 4, minus lambda times I, which is 1, 0, 0, 1, because this is a 2 by 2 matrix there. Okay? And that's going to be equal to 0. So far, so good? Now, clean this up. This would be the determinant of, now how do I subtract two matrices? It's going to be 2 minus lambda times 1, which is 2 minus lambda. 1 minus lambda times 0, that's just 1. Negative 1 times minus lambda times 0. Lambda times 0 is 0. Minus 1 minus 0 is minus 1. And the last one is 4 minus lambda times 1. That'll be 4 minus lambda. So, understand this. I wrote it like this, but if you want to also look at it as such, it's the determinant of A, which is 2, 1, 2, 1, negative 1, 4, minus lambda 0, 0, lambda. And when you subtract off lambda that's on the diagonal, it only affects the diagonal, and the other parts of the matrix end up being the same. Does that make sense? It only affects the main diagonal. So you can get quick at this stuff. Now, we want an equation out of this guy. So here we go. Take the determinant. How do you take a determinant of a 2 by 2 matrix? You do main diagonal minus off diagonal, right? So this would give you the equation 2 minus lambda times 4 minus lambda minus 1 times negative 1. Main diagonal minus off diagonal. But remember, it's set equal to 0, so you got an equation. Clean it up. I would FOIL this part out. 2 times 4 is a 8. 2 times minus lambda is a minus 2 lambda. Minus lambda times 4 is a minus 4 lambda. Minus lambda times a minus lambda is a plus a lambda squared. Minus 1 times a negative 1 makes it a plus 1 equal to 0. All I did was FOIL it and combine like terms. So let's combine some more like terms. This will give me lambda squared minus, combining like terms, 6 lambda, combining like terms, 8 plus 1 is 9, plus 9 equals 0. This, right here, when you set the polynomial, which is what you're going to get, equal to 0, this is what we call the characteristic equation. Does that make sense? Now, how do I find Mr. Eigenvalues? Well, to find the eigenvalues, you're going to take this guy. So here it is. You come up with a characteristic equation. Step number 2 is this. Characteristic equation equals 0, solve for lambda. So you've got lambda squared minus 6 lambda plus 9 equals 0. It's a quadratic, only because it was a 2 by 2. 3 by 3 it would be a cubic. 4 by 4 would be a quartic, degree 4 polynomial. 5 by 5, 6 by 6, you get the deal. These polynomials are going to get large on you here. But this one's quadratic, and because I made it up, hopefully it'll factor. So here it is, lambda squared minus 6 lambda plus 9. Lambda, what times what is 9? They add up to be 6. Got to be 3 and 3. The signs is a plus, so they have the same sign. Middle terms are negative, so they both got to be minus. Then you set each factor equal to 0, and you solve, and you get lambda equals 3, and you'll notice, and I'm going to code this, this is a double root. So it was a quadratic, so I was expecting to get 2 answers out of this guy, but they happen to be the same answer. This is a double root. So keep going. Got your eigenvalue. There's only one of them for this matrix. So now, step number 3, we need to come up with, find the eigenvector. How do I do that? To find the eigenvector, go back to this. The original equation, which is A minus lambda I times V equals 0. Go back to that. Okay? And plug in. A was what? What was A? It was 2, 1, negative 1, 4. Just reminding myself there was A. Minus lambda times I, 1, 0, 0, 1. Okay? Parentheses around it. Times vector V is equal to vector 0. I'm going to clean this part up right here. So I'm gonna write him right here, just follow the arrow so I can have more room over here. This would be 2 minus lambda, 1, negative 1 minus, I see negative 1, sorry, negative 1, and then 4 minus lambda, times vector v would be equal to vector 0. Does that make sense? Combine my terms. But what was lambda equal to? 3. So plug in 3. This would be 2 minus 3. I'm trying not to skip any steps, but I do most of this work in my head, just to be quite honest with you. But I'm plugging in lambda equals 3 here. Times this vector v. I'm going to relabel vector v as, let's call him AB. There's my guy. And it's got to be equal to the 0 vector, which is now 0, 0. This is going to give me negative 1, 1, negative 1, 1 times vector AB equals 0, 0. Does that make sense? How would you solve this guy here? Augment the matrix. Negative 1, 1, negative 1, 1, augment with 0, 0. I'm going to do reduced echelon form, but I want you to look at this thing and tell me one thing. Look at the first row, look at the second row. What do you notice? Same thing. When I do reduced echelon form on this thing, you're always, can you put this in your notes? You always get a row of zeros. When I do reduced echelon form on this guy, I would make that a pivot, make it 1, negative 1, augment with 0. But this would be 0. I'll multiply this one by negative 1, added to this one. Because they're the same thing, you're always going to get a row of zeros. Remember, this matrix has a determinant equal to 0, which means it's it's singular, it's non-invertible, so when you row reduce it, you always get a row of zeros. So now here we go. Back to my equation, this means A minus B equals 0 from that first equation. Solve for the pivot. A equals B, and B would be equal to B because it's free. You with me? So I end up getting the vector AB is equal to, you can factor out the B, and what do we get? 1, 1. And you've got your eigenvector. What is the eigenvector? It is the vector 1, 1. Always expect a row of zeros on these guys. So, question. What's that? This one right here? Oh. Okay, yes, but I like to have a pivot right there. So multiply that row by negative 1. Multiply this row by negative 1. What do you get? 1, negative 1. I just did that in my head. Okay? I made him a pivot, and because they're the same rows, I did row 0. So I did 2 moves at once. I made him a pivot by multiplying by negative 1, and added this row, made it 0. And you're always expected to get a row of zeros. If you don't, you screwed it up. There's a math thing for you. Don't worry, we got a lot more problems to do when we talk about this on Tuesday. Study hard, and I'll see you guys then.